First of all, thank you for having me. I'm Alex. Surprisingly, I've been in the space now for like 6 years, full time. This is kind of the wrap up of about 2 years of work. By the end of this presentation, I'm going to talk about how we went from fuzzing or setting up fuzzing suites for Solidity smart contracts, which is basically a specific type of testing that will typically take us about 4 weeks. And we managed to bring it down to less than a day, obviously with caveats. In terms of who I am, I co-founded Recon with Antonio Vigiano. We are lead security researchers. We work with Spearbit, Code Arena, Sherlock. More recently, work with Liquidity, Centrifuge, and hopefully we'll get to announce on our customers soon. I have about $500,000 in awards, and last year, through the technique that I'm talking about today, I actually prevented an exploit on mainnet and saved about $20 million from a great protocol. If you guys want to support us, we actually are live on Giveth. We have an invariant testing extension. Fundamentally, given Visual Studio Code or given Cursor, you just click a button and it automatically sets up all the tests. So the stuff that I'm going to talk about uses the extension as a prerequisite, but in theory, you could also do that manually. We also have about, I think, 1 spot left on invariant testing bootcamp. It's something we teach with Rare Skills. I'm going to be the teacher for this. Last 5 weeks, and it's starting Tuesday at 3 p.m. Central European Time. And fundamentally, the AI that I'm going to present today does the job. And then if you want to go deeper, obviously, you can benefit by doing the bootcamp or working with us. So the foundational insight that builds on top of all fuzzers is this key idea that I say we pioneered, but it's not correct. But fundamentally, if you use a fuzzer like a Kidner or Foundry, you can set up your test in 2 ways. One, in which you take the contract that you want to test, and then you just release the fuzzer against it, which we will call, I guess, the direct approach. Or you can take the approach that we use, which is the idea that we're going to deploy one test contract, typically as the setup function, something you should be familiar if you use Foundry. And then from that test contract, we're going to deploy the entire system under test, which means that this gives us all the contracts that are in the universe. We basically have access to them. We know what they are. We know the variables. We know the constants. We know the config. So that gives us a very controlled environment. And the reason why is because if you don't do this, if you start, say you want to test a Uniswap pool, actually the most common invariant testing example is by Horse Facts, and he uses WEF. And basically, it ends up, or Horse Facts was forced to basically mint tokens and deposit, or basically create macros in order to write his tests. And that's a pretty complicated approach. And so, to simplify things, we basically just deploy a test contract, deploy everything else, and then we expose every function that allows us to interact with the system. The downside is that we end up having a very verbose system. So if you look at the folders from some of our tests, they're very verbose. But the advantage is that it's very simple, and fundamentally it's just easy to manage, it's easy to track, and it's something that ends up resulting in very simple to read proof of concepts. So how do we perform this testing algorithm? We fundamentally scaffold, which is the act of doing the deployment, setting up all the tests. Then we run the fuzzer, meaning we run the tool that gives us some sort of a feedback. And then we evaluate coverage, meaning we evaluate how many combinations, how deep did the fuzzer go in terms of testing. The fundamental issue with this is that the fuzzer is unable to explore all combinations. So if you're familiar with formal verification, a test will time out, meaning that the tool basically gives up because it can't make a decision, or basically can't falsify the assertion, but at the same time it can't come to a conclusion. Whereas the fuzzer, the form of timeout for the fuzzer is that you don't get coverage. And coverage, if you're not familiar with it, just means that the lines in your contracts are green, which means that they're being covered, and they're being called by the fuzzer. And so the way in which we guide the fuzzer is by clamping, where clamping means that instead of giving the fuzzer the ability to explore basically an infinite amount of possibilities, we simplify them. And clamping sounds like a very simple idea, but it actually hides these two levels of clamping. There are, and by the way, they're all tied to limitations of the tools that we have. They're not fundamentally something that, I think if we had better tools, we wouldn't have to solve for this. But the two ways in which we have to guide the fuzzer, one is tied to the dictionary, which means that we basically give it a specific value. For example, the address of an actor, the address of a token, the address of a vault, some constant. And the fuzzers try to do this through what is called constant mining, which means that they basically inspect, for static analysis, they inspect the contracts, the bytecode, and they extract some constants. And then the other part is tied to basically the fuzzer will listen to return values of functions in order to figure out what to use. But it typically will fall short, and so you can see here we use getActor, which basically is an abstraction that allows us to get the current user that we're using. And then amount, I put it there just to talk about the clamp-based clamping, where if you imagine that the fuzzer is basically a hose that can try every possible combination, then any possible input that uses an amount of tokens that is above the balance of is complete waste of an input. And so clamping fundamentally, when it comes to the consume-based relations, is tied to identifying that and telling the fuzzer not to use it. And so clamping introduces bias because obviously as you hard code things, you're no longer testing everything, you're only testing a subset. But and so the technique that we use is what we call creating effectively a subset, where the clamped handler, which is basically just a function that will call another function in our target, is forced to use the unclamped handler, meaning that instead of creating these, how do I say it, like the unclamped handler will literally just receive these inputs and perform a call to the target, whereas the clamped handler will basically have dictionary manipulation and other form of tracking to make it so that the fuzzer is more efficient. And the key goal with this is that this is a non-destructive operation, meaning that we can write as many clamped handlers as we want, and even if none of them works or reverts, they fundamentally don't mess up the fuzzer. And then at the same time, because we call the unclamped handler, we are not creating a bias that would allow, force us to miss a bug. So for example, if you had if you have a donation handler where you would just transfer tokens to some address, if you hard code all the addresses, then maybe you're going to miss one. For example, donating to the actual vault, and that will lead you to being unable to ever possibly find a bug. Whereas using this technique makes it so that even though the fuzzer will struggle to try these combinations, it still has a chance. And before I show you the I part, we need to talk about how you will evaluate success or how you evaluate progress in fuzzing, which is tied to coverage. And, but coverage doesn't mean that every line needs to be green. Coverage means that only the meaningful lines need to be green. And so we call standardized coverage or standardized coverage as the coverage that pertains only to non-view functions, meaning we are examining only functions that can alter state, because those functions that alter state basically alter the underlying values, the underlying variables, and they basically allow us to run assertions on top of that. An even better way to evaluate this would be to use sensitivity analysis, which will fundamentally mean that we would mutate the target contracts and then replay the fuzzer with the corpus against these mutated contracts, and we will then evaluate the coverage as a proxy for the quality of the testing suite. As far as I know, nobody did it, but I think it's a pretty obvious next step for improvement. But to kind of put it all together, this was kind of the non-AI part of the talk, where when it comes to fuzzing, we have kind of these different phases. We have the scouting phase, which means that you have to decide what you're going to fuzz and how. Then we have the setup phase, which means that you're going to basically deploy your target contracts under the paradigm that I mentioned, where you deploy one contract that then deploys everything that you're going to test. Then we have the coverage phase, which means that we want to ensure that the fuzzer tests these combinations, and that typically takes a lot of time. This is why most people don't use this technique, is because coverage takes forever. Then we have the property specification, which obviously the quality of the properties that you implement will determine what you find. However, properties tend to also be something that, just like clamped handlers, you can just throw as many properties as you want, and you're not going to have negative side effects. And finally, you want to iterate, meaning you do some sort of a reflection, you figure out your understanding of the system, and then from there, you decide if you need to improve the coverage, improve the combination, improve the setup, or improve the properties. And so basically what we did is we had AI do this. And it's not a coincidence that I separate this into different phases, because all of these phases will then map out to a list of prompts, a list of commands, and a list of operations that the AI does for us. And so the key ideas, I'm sure you're all using AI everywhere, but the key idea is that the only thing you need for AI is prompts. And this tends to fail fairly quickly, especially with less sophisticated models. Our framework works with, it's been working really well since Sonnet 4.6. So as of now, basically any AI can use our framework because of using structured outputs, chaining prompts, and adding condition. And with that said, I'm introducing the Recon Magic framework, which is a completely open source, completely free repository that contains a bunch of things I'm going to talk about. We have fundamentally an orchestration framework to run AIs, a bunch of tools, a bunch of scripts. This shouldn't be particularly new if you ever used AI professionally. And then what we did, though, is we applied this to fuzzing, to make it so that we can give the AI basically a one-liner prompt of what we want to test, and then the AI can then go through the phases I mentioned before of scouting, deciding how to set that up, doing the setup, getting to coverage, writing the properties, and then basically giving us a feedback there. I'm going to have a link to the GitHub at the end, but the way the framework works is if you want to dig deeper, there's all the internals. So if you don't care, you don't have to look at that. It doesn't matter. But fundamentally, there's going to be a way to handle it's basically a non-Turing complete framework that makes it so that we don't have infinite recursion. We don't have nested recursion either, so that we avoid effectively burning all our tokens. And the key components are really going to be programs, which means that we have a bunch of static analysis tools that we can run as CLI so that they're all portable. Anytime you just install the framework into a new machine, you already have access to those. Then we have the prompts, which effectively do the heavy lifting. And then these prompts and programs are combined into what we call workflows, which are basically just these very simple JSON files that effectively tell the framework how to operate. And using this orchestration layer makes it so that we can combine CLI tools, tools that we have, MPX tools, running the fuzzer, running AIs. You can use LangGraph. We used to have components in LangGraph, component using open code, etc. And fundamentally, it's basic as if we are moving a factory, right? Because the JSON file effectively specifies how the factory will behave. And then you just point it at a code base and you just run it. So it's very easy to extend this. And if you want to install it, you basically just install a Python script. And then you run it in this way where you specify the workflow name. And then if you, obviously, you should run this into a sandbox environment, but you can just use the dangerous flag to effectively have it do anything. And then you can also dump logs, which means that anytime you run AI, it's going to automatically dump all logs into a folder so you can check every single decision, every single step. And this is how you would run an AI. You can see it's extremely straightforward. We basically just tell the AI to read a prompt, and then internally in the core of Pi, anytime we use this type of semantics, it actually automatically takes the contents of the markdown file and give it to the AI. But the reason why I mentioned this is because because of the history of how we built this framework, which was based on effectively just creating a few prompts, telling Claude, read the prompt and execute, and then iterating over that. And so for us to go from, basically from a single prompt to an actual framework that works, that's what it took, and that's why it's built this way. And so if you end up using this either for fuzzing or other purposes, that's really the way the way you want to work. Is you want to just give the AI one prompt, evaluate the result, and then you iterate, and then over time you start chaining it. Our framework allows us to add conditions, meaning we can read a file, check if the AI made a decision, and put some content in a file and decide where to branch to. And we also have some blockers to prevent infinite recursion. Let's talk about kind of the things that can go wrong if you try to expand the AI. The most common mistakes we ever ran into was tied to relative paths. So if you, for example, if you specify /magic versus /magic versus magic, based on the model, you would actually get different results. So from my experience, you want to experiment with that. Another thing that happened frequently, it tends to happen less now with smarter models, more expensive models, was tied to the consistency of format, consistency of output. And so what we used for that is called structured output. It's a very common technique, but fundamentally we force the AI to write down every decision that it makes into another JSON file, which we call the decision. And so we make it so that we can evaluate what the AI decided by looking at its output in a more deterministic way. Another thing that tends to happen with fuzzing especially is that the AI will fixate on using the wrong command. I don't know if you've seen that with Foundry, but it basically hallucinates a flag, and then it will try using it forever. And this is really why we combined hard-coded commands with AI, because by doing this, anytime the AI keeps messing up how to use our fuzzer, we just hard-code the command, and so we don't have to deal with it. And this makes it so that we can use a cheaper, dumber model, and once those models are smart enough, you no longer have to worry about your model becoming obsolescent or stuff like that. And so this is really hopefully a very useful insight, is that once you effectively make those decisions consistent and you refine them into a data structure, then obviously the AI is going to be more reliable. But after that, what happened after that is that when you refine some decisions to a point that you can express them as a data structure, then likely you can build a CLI tool. And so if you look at our repo, you'll find that some of our tooling, for example, evaluating the coverage, started as asking the AI to basically look at the coverage file and tell me what it looks like, to give me a grep to evaluate it, to a tool that basically evaluates it, so we don't have to deal with that level of slowness, that level of extra complexity, and those additional costs, because obviously we have tokens. So given that, if you want to get started with fuzzing, you can obviously use our extension. You can also look at our boilerplate, and then you would use the Recon Magic framework to effectively do all of the work for you. It can be, obviously, it can be very overwhelming if you've never tried it, but at the same time, we basically boil down, I don't know if I have a link to the article, but basically we boil down what was 4 weeks of work into something that you can run in 4 hours. And we have a full benchmark here, run on Liquidity, V2's governance, Superform periphery, Monolith, and Aave v4. And basically, these are kind of our results, where the blue means the unclamped. Like if you use our tools and you press a button in the extension, that's what you're going to get. And then the fuzzer will struggle to get any higher coverage. Maybe you can get higher if you run it for a very, very long time. But instead, if you just have the AI add the clamping, that's what's going to happen, is that the AI is basically able to reach 100% coverage in the majority of code bases below 2,000 lines. And then for code bases that are way past the 2,000 lines, it can end up having some issues, but it will always be a net positive because of what I said at the beginning, where the clamped handlers are a subset of the unclamped handler, which means that you're not distracting or ruining the fuzzing suite. You're just adding a few extra lines to help you get to that. And so this kind of boils down to the remaining issue, and I want to kind of mention something that Elon Musk said on AI, that he said that you're not going to have programs, you're going to abstract the programs, and you're just going to tell the AI what to do, and the program will be implied. And I think with fuzzing, we have really the same idea that everything we built is probably the most verbose, most, at the same time, most visible, most understandable approach to fuzzing. But in the future, what I believe we should do is take all of these ideas of having the AI create solidity handlers, writing more code, etc., and just put all of that into the fuzzer. Because once we know that we're going to test systems the way I mentioned, and we know the algorithm that the AI is going to take, then we can just put all of that algorithm into the fuzzer and basically give it as a default to most people. And the key problem that we're still left with is called dynamic linking, which is the idea that given some specific function, some specific contract and some specific function, we want to be able to link that, those specific inputs to either some constant or some other value from other parts of the system. Since in fuzzing we always deploy the entire system under test, we basically know what the universe looks like. So the idea that the fuzzer can't do it is just not true. It's just it hasn't been tried. And we're going to be open sourcing another tool that does this eventually. So if you want to give a shot at our AI framework, it's here at Recon Magic Framework. That's the link. And then we also recently open sourced a Echidna clone written in Rust. It's basically a 10 times faster Echidna at Recon Fuzzer. So you can give it a test as well. And I also want to give a big shout out to my team that spent 6 months building this. After 2 years of research, we have Nicanor, Not, Davito, and Gondar. If you want to check out more of our work, you can go on the QR code. Thank you for having me.
Thank you for your speech. Do we have any questions to the after?
Yeah, great talk. So I saw that Claude and Codex recently started to restrict cybersecurity applications. So you need to upload your personal information in order to keep using it. Have you seen any refusals in the AI saying, no, I'm not going to do this because it looks like you're trying to hack a contract?
No, I've never run into any blocker. My team uses AI a lot more. They're doing a lot of bug bounties. I don't tend to use AI all the time to like give me an exploit. But the way we chunked our work is that every step is separated, and then there's only some high level of context, such as you're doing a fuzzing engagement. This is phase 1, this is phase 2, this is phase 3, or like I'm looking at the relation between functions, give me a list. So I believe that we wouldn't run into that. Not only that, if you follow the approach that I mentioned, because as I mentioned, the way we built the framework is we literally had a prompt, and now you see they're all divided into multi-step. But originally there was one prompt, and then the AI will fail at some point, right? And you're like, oh, Control-C, stop it, and see what's going on. And then from there, if you find these blockers, these security blockers, you basically will chunk the task into the steps, and then you will identify the step that triggers the blocker, and you will stop it. And most of the times you'll find that if you segment the task, there is no task that is impossible for any model, even if we use the old school open source GPT, whatever it's called, we would actually be able to have that be successful, provided that we spend enough time refining the prompts and the tools. So the idea that it can't be done with the current tech, or that we don't have like, a super intelligence, is just incorrect. But then at the same time, the amount of work, if you just look at our prompts, it took us 6 months to make it reliable. So the amount of work that it takes to really streamline that stuff is enormous.
Thank you.
Thank you so much for your talk. Unfortunately, we don't have time for any more questions, but if anyone will have them, feel free to ask the author later. Thank you so much.
Thank you.